Okay, let's continue with our lecture on linear vector spaces. We have been looking at the various properties of eigenvectors, and let's take a quick example before proceeding any further. So let's consider in R2, let's consider a matrix in R2 which is producing a rotation with an angle theta. The matrix A is given by elements cos theta, sin theta, minus sin theta, cos theta. This is the well-known matrix which produces the rotation. Let's find the eigenvalue for this matrix with characteristic equation. That is determinant of lambda minus A equal to 0. So from this we get determinant of cos theta minus lambda, sin theta minus sin theta, cos theta minus lambda equal to 0. When we explicitly write the polynomial, we get cos square theta minus lambda square plus sin square theta. The solution for lambda is cos theta plus I sin theta. So this seems to be a complex eigenvalue. So we know that mathematically it is possible to have a complex eigenvalue, but what is the physics? How do we get the complex eigenvalue for the rotation? Rotation is very much physical. How do we see the rotation which is giving rise a complex eigenvector? You need to explain this, and the answer can be written on your notes and uploaded with your regular notes. Let's go ahead and see another example. Here again a matrix in R2 with the matrix element A is given as 3, 1, 0, 3. Let's find the eigenvalues first. We can straight away write down the characteristic equation with the determinant of 3 minus lambda, 1, 0, 3 minus lambda equal to 0, and polynomial simply reduces to 3 minus lambda square is equal to 0, resulting in eigenvalues 3 and 3 repeated eigenvalues. So it's not surprising, you can get the eigenvalues, repeated values. So is it possible to solve for the eigenvector? Let's see. We find out the eigenvector simply substituting the eigenvalue in the eigenvector equation and solve for the component from getting the n equations. So we have 3, 1, 0, 1 into V1 and V2 components of first eigen vector. Here we put lambda into V1, V2, with lambda is equal to 3. When we solve this, the second equation gives V2 equal to V2. So that means it doesn't give any extra condition. V2 remain arbitrary. Now let's solve the first equation. For lambda is equal to 1. We get 3V1 plus V2 is equal to 3V1. This implies that the V2 has to be 0. Now proceeding with this, we see that there is no condition on V1, so that remains free. So we take the value of V1 to be any arbitrary number, but let's fix it to 1, and V2 have to be 0. What about the second eigenvector? It is not possible to find out the second vector here because both the eigenvalues, which are same, have been already used, and we have not got any condition for V1 while we have already fixed V2. So that means we cannot have any more eigenvector. So can you explain what is going on here? What happens when eigenvectors are repeated? So your comments can be put in your notes and uploaded on the Another example. So another example goes like this. Again, find the eigenvalue for the matrix in R2, that is A is equal to 3, 0, 0, 3. It's a diagonal matrix. You could have a different diagonal elements, but you could have them same too. Let's find the eigenvalues of this matrix from the characteristic equation. What we get is 3 minus lambda 0, 0, 3 minus lambda equal to 0. That means 3 minus lambda square is equal to 0. Again, we get lambda is equal to 3 and 3. That is repeated eigenvalues. Let's find the eigenvectors. We get 3, 0, 0, 3, v1, v2, and lambda into v1, v2. So let's put the different eigenvalues. In this case, they are same. So let's solve this. So what we have is for lambda is equal to 3 and for lambda equal to 3, we get the condition v1 is equal to v1, v2 is equal to v2. That means we have a full freedom to choose v1 and v2 as per our wish. So we could choose v1, v2 is equal to 1, 0 for lambda is equal to 3, and u1, u2 is equal to 0, 1 for lambda is equal to 3. So this way we construct two separate and linearly independent orthogonal eigen vector. So how this case is different from the previous one? Of course, it is depends on the nature of the matrix. Diagonal matrix is the most convenient one to solve. Please write your comments what is going on in the three examples and upload on the VLearn along with your notes. You don't have to be separate. In the same note you write your answers too. Let's go to an important problem in the eigenvalue problem, that is called the eigenvalues of a real symmetric matrix. A symmetric matrix is a one which has a property that the A transpose is equal to A. That means a matrix is symmetric about its diagonal element. Diagonal elements can be anything, but the upper triangle part of the diagonal element should be equal to the lower triangle part of diagonal element. So this is what we call the symmetric matrix. The eigenvalues in general can be complex that we have seen. So we should allow to have a freedom to handle the both real and complex eigenvalues. So we say that the complex conjugate you are all familiar with is represented by lambda star. If the eigenvalues is real, the lambda star equal to lambda. If it is a complex, then you would have a lambda star is different from the lambda. So eigenvectors also same thing can be done. If the eigenvalue is complex for the real matrix, eigenvector also become complex. Then simply taking complex conjugate will not work, because we know that the complex conjugate when properly not handled, you would not get the dot product as a positive real number. So we have to do what is known as Hermitian conjugate, which is very commonly done for the matrix with the complex element. So what we have is a V and a V dagger. In terms of column notation or our matrix notation, if V is a column vector, then V dagger is simply a complex conjugate and transpose done together. So they do commute. That means you can take a transpose first and complex conjugate later. So that way the scalar product becomes sum I is equal to 1 to n vi star, which becomes meaningful in the sense it becomes a positive definite number. In terms of our bracket notation, we have vectors are denoted by a ket, and whose complex conjugate would be a bra vector. So everything is built into it because it is suited for doing the complex vector space. So it is simply given a one ket which incorporate transpose as well as complex conjugation, so that the dot product v dot v becomes sum I is equal to 1 to n I vi star. So we also have, we can now do this operation on a matrix operating on a ket vector and taking the Hermitian conjugate. Then we simply get the bra vector operating on its Hermitian conjugate. In this case, our matrix is a real and symmetric, leads to Hermitian conjugate A itself. So that is what is represented here. This becomes this. Okay, so because A is real and symmetric. Now we show that the eigenvector corresponding to the eigenvalue lambda. Let V be the eigenvector of the matrix A with the eigenvalue lambda. Then that is expressed in terms of equation like this, and then we go over a series of expressions which indicate all the properties of our real and symmetric nature of the matrix and its eigenvalue. Let's take the V dagger. Let's take the operation of a dagger operating on the bra vector V. Let we start with that, and then because it is a real vector, the complex conjugation has no effect, so we get the result that the A transpose operating on the V. Now we see that the A is a real matrix, so the transpose itself has no effect on the matrix A. Then we left with the A operating on V leads to the eigenvector. If the eigenvector is a complex, then it would be complex conjugate would be taken, because from our definition we have a dagger is becomes a ket, and lambda becomes a lambda star. So this is a simple identity which we are going to use. So let's go ahead and try to see the eigen values of a real symmetric matrix. Let A be a symmetric n cross n real matrix with the eigenvalue lambda and corresponding eigenvector V. Now let's do our calculation separately across the wall and with the two expressions, and see what happens. The first expression is a lambda multiplied to V dot V. On the other side of the wall, we have a lambda star multiplied to the dot product V dot V. We are here in general assuming that the lambda is complex, and then see what kind of constraints we get. We can absorb lambda inside because it is a scalar in the either side of the wall. Now in this case, these two together gives the vector A, because A is having a lambda as an eigenvalue and a V as an eigenvector, and this expression leads to this. On the other hand, this expression here leads to A, because for the bra vector, lambda star is the eigenvalue with the matrix A. So once we have this, we have a same expression across the wall. Now we can break down the wall and compare how does the expression leads to interesting results. Let's subtract the expression from both sides of the wall, and what we get is lambda minus lambda star into V dot V should be equal to 0. We have already assumed that V dot V is not 0, because we are taking a meaningful eigenvector, and that result to lambda minus lambda star equal to 0, implying that the lambda must be the real quantity.